Yeah. In 2016, when I was finalizing my first paper, I came to my supervisor room, Robin Walbina, who is just sitting here, and I asked him that how can we use the LiDAR data directly, for example, to classify the forest structures? And he told me that, yeah, well, we have submitted our paper, and then he gave me his draft version. So in this study, we are trying to estimate above ground biomass from the forest structures detected directly from LiDAR data. And we are comparing it with the overall data without any classification. So we all know that LiDAR produces accurate canopy information, and it measures the vertical heights of trees. And the metrics derived from LiDAR data, they are useful and they are used to predict various forest attributes. For example, volume, basal area, stand structure, and many more. I will mention two LiDAR metrics, the L-coefficient of variation and L-skewness, that can be used to obtain forest structures directly from LiDAR data. So LCV is actually a ratio between the second and first L moments. And L moments are similar to the conventional moments like mean, variance, skewness, and kurtosis, but they are robust and smaller sample sizes, and they have fixed intervals. For example, the LCV is varies from 0 to 1. And LCV is equivalent, mathematically equivalent to Gini coefficient. And Gini coefficient is an indicator that evaluates inequality among trees growing in a forest. So this LCV can be used to separate even and uneven size forest structures. The second L moment is the ratio, the L-skewness is the ratio between third to second L moments, and it is bounded between -1 to 1. And this can be used to evaluate the canopy closure. So we can use L-skewness to separate open canopies, euportic areas, or oligoportic areas like closed canopies. Okay, so the L-skewness and L-coefficient of variation, they are useful for structural mapping, but the structural complexity of forests, so it may cause difficulties in modeling the above ground biomass. For example, a same model applied to a large area and different forest structures, they may not be appropriate. If we apply a same model to both the even and uneven size forest structure or dense or sparse forest structures. So what if we classify a forest into different structures, we apply a separate model to each structure, and then we compare it with the overall data without any classification. So will it improve our biomass estimation, and the biomass estimation will be reliable or not? The study was conducted in boreal forest, Finland, and the dominant species are Norway spruce, Scott pine, and birch species. And we have 244 field plots collected from different stand development classes like seedling, sapling, and advanced mid-shade and seed trees, and multi-storied, and approximately equal number of field plots were collected from each strata. And then we applied rule-based classification to separate different structures. So we used L-coefficient 0.33 because it denotes represents a maximum entropy, and we separated even and uneven size forest structures. We used L-skewness 0, which represents the symmetric distribution and we separated the open and closed canopies. For above ground biomass estimation, we used locally developed equations for each for Scott Pine, Narrow Spruce, and birch equation was used for like birch trees and other deciduous species. And we calculated tree level above ground biomass, and we converted it to the plot level and used as a response variable. We had many LiDAR metrics, for example, more than 100. So we needed to select a best subset among those predictors. And for that, we used a reg subset package of R. And then we used KNN method, and we used the best subset, and we predicted the above ground biomass in each forest structure and the overall data. We use cross-validation, k-fold cross-validation. So in our case, we use 10-folds cross-validation. Like we divided the data into 10 folds, 10 groups. We removed, for example, the first one fold. We fitted the model with the 9 folds, and we predicted the first one, and then we removed the second one, and so on. We calculated the RMSD and mean difference between the predicted and observed values to calculate to find the precision and precision and bias. We also used hypothesis test on the one-on-one correspondence between the predicted and observed to find this correspondence analytically instead of visually. We also used sum of square ratio and R to R ratio. Sum of square ratio is the ratio between sum of square obtained from the predicted and observed values, and the R to R is the R squared ratio obtained from the predicted and observed values, and the limit, and this SSR and R to R were used to ensure that our models are not overfitted. So the limit was 1.1. If the values of the SSR and R to R are less than 1.1, so the models will be not overfitted. So these are our initial results. So we can. So these are the L-skewness line and the L coefficient of variation boundary, and these are the above ground biomass estimated in each development class, and we can see that the seedlings were separated as even size, and also the mature trees and the young trees in advanced stage, they were also separated as even size forest structures. But the saplings were separated as uneven size, and probably it's because of the lower ALS returns and which increase the L-skewness. So the L-skewness is high, and maybe it's because of these values. And the other one is like the shelter root, which is mostly like even size, but here most of the shelter root, they were also separated as uneven size, and probably it's because the omission of the understory. And our point density was 0.91 points per meter square, and any point density lower than at least 3 points per meter square are not reliable for structural classification, particularly for the Gini coefficient. Then we compared the basal area and diameter distribution obtained from the GC of basal area and GC of LiDAR. So in the top we have the GC basal area based even size forest structure, and the down we have GC LiDAR based even size forest structure, and we can see that the distribution, the basal area and the diameter distribution are quite similar. Here, like if we calculate the Gini coefficient from basal areas, so the maximum entropy reaches at 0.5. But if we calculate the GC from LiDAR, tree heights, the maximum entropy reaches at 0.33. And similarly, the uneven size forest structure, we have almost like similar basal area and diameter distributions. The estimated and predicted above ground biomass, the mean above ground biomass was like similar in all cases, like 87 million gram per hectare, 89, 102, 105, and so on. And the accuracy assessment of the estimated and predicted above ground biomass, we got like under prediction in all cases, right under prediction. But in the uneven and the closed canopies, the under predictions like decreased as compared to the other values. And the precision is like, we got like similar precision in uneven in eupotic areas, but it decreased in the oligopotic or closed canopies and the even size forest structures. The SSR in R2R values were below 1.1 in all cases, so the models were not overfitted. In the hypothesis test, the one-on-one correspondence values are here, and it also showed the under predictions. So L coefficient of variation in combination with L-skewness, it could be used as analogous to the Gini coefficient of basal areas for structural classification. L-skewness will separate the even and even size forest structure, and the LCV will separate even and uneven size structures, and the L-skewness will separate closed and open canopies. In the above ground biomass estimated, they are like reliable, and it can be useful for better forest management planning and understanding of natural dynamics within large geographical areas. Thank you.